All right. I hope everyone had a nice Øredev so far. Last day, almost over. So I hope the next 40 minutes will be worthwhile, and I can show you some of the stuff we have been working on. So this session is more about advanced mixed reality development topics, mainly focusing on HoloLens development. And we have been doing HoloLens development since 2015. We were part of the first 5 agencies that got access to the hardware and the SDK, and an early adopter program from Microsoft. And since then we have developed dozens of applications for different clients, really mainly focused on enterprise and professional use case scenario, and not so much on entertainment and games. And in this session I will going to show you a quick demo. So we will develop a little application where I'm going to show you a hand proximity interaction. So how can you directly touch holographic objects, right, instead of using gaze-based input. Then I'm going to show you some of the applications we worked on and talk about the lessons learned and give some best practices, what we learned while developing those. And at the end, I will show you my top 10 HoloLens development recommendations. And yeah, should be fun. My name is Rene. I'm Director of Global Innovation at the company Valorem. And I run the immersive experiences team there. My background is really development. I'm a developer, actually, and have been doing VR, AR, and mixed reality, well, VR and AR definitely since like 10, 15 years. Also did some open source projects there. I'm Microsoft MVP as well. If you're not familiar with that, that's an award Microsoft gives out to independent experts. I'm not getting paid by Microsoft to talk about anything here. And just enjoy the technology and spread the word, if you will. And that's what's getting honored by Microsoft. And like I said, I'm involved in some open source work here. A quick video about the company Valorem. We are headquartered in Kansas City, US, and Seattle. I actually work out from Dresden in Germany. We have been doing lots of UX development and Xbox application, Kinect work, and so on, and that's why we got in this early adapter program for the HoloLens in 2015. But we also do Azure and Office 365, but of course that's a different team. But we span the whole spectrum, if you will. Again, quick video, less than a minute, but shows you some of the team members and stuff we work on and how we do the work there. Unfortunately, the audio didn't work. We tried a couple of things, so I have to sing. Or join me for singing. Well, yeah, you see, oh, there's a HoloLens, ooh, and there's a logo. Yeah, some of the team members, like typically, design, we start with sketching and interaction design. A couple of snapshots from some applications we work on. And some of those things. I'm going to show you a bit more about that app and tell you how we developed this one. That's Javier, creative artist, creative art director, actually. 3D modeling, we do that as well, because we need 3D models for visualizing in 3D. All right, good. So a quick word about the mixed reality spectrum. So I gave the slide to Laurent. So who of you actually attended Laurent's session just before that one? Good. So we can skip over those kind of things. Just real quick, mixed reality spectrum. That's Microsoft's definition of what is mixed reality. AR on the right, on the one side, VR on the left, on the other side. This is actually not just made out of thin air, right? So this is based on a scientific paper that was released more than 20 years ago by Milgram and Kishino, and that defines the whole continuum. So Microsoft said, okay, let's call this device mixed reality, and then they released those VR devices like the Acer and so with their partners. And well, I wasn't a huge fan that they called them VR devices as well. Mixed reality devices as well. They are VR devices, so why do you call them mixed reality? We have been using the term for this device. But I see a vision here. So thinking about maybe in a couple of years, maybe in 5 years, and again, that's my own interpretation, right? That's nothing I hear from Microsoft. But I'm involved in the industry, so I think I'm not too far off there. So what I see in a couple of years, we will have one device that spans the whole spectrum. So why not have a device that can basically shut off the whole visor completely, and then you're fully immersed into VR experience, right? And then you can dynamically switch it on, and then you have your AR experience. So I see a vision here, and that's why we call it mixed reality spectrum. Probably most of you have seen that. We have different devices at the moment. So the HoloLens is really goes to the middle quite a bit. The immersive device, the occluded one, goes only a bit here to the VR spectrum. But again, I think in a couple of years we will have one device that spans the whole The samples, you know them, a couple of games from Microsoft. Really, the HoloLens is a very immersive device. It can really transform the room you're in into a different setting. You're familiar with the HoloLens already, I'm sure. Just a quick word about it. Well, I'm still blown away what the device can do, even after using it for 3 years. And I can tell you I tried a couple of other devices. I think I tried everything on the market so far. And nothing comes close when it comes to the inside-out tracking, the spatial mapping, and how the device tracks the room to make sure that the objects, the virtual objects, are stable. Nothing comes close. Like the Meta and Decri and so on, all those competitors, it all jitters. It moves. When you move yourself, it isn't stable. And that's what Microsoft really got perfected in that device. And that's what they sold or licensed out to the OEMs producing those immersive mixed reality devices, right? The Acer and so on. So they license out that inside-out tracking technology because it's so amazing and it's still leading the pack, if you will. And how can they do that? Well, they have this custom chip, they have this HPU. That's the only way to get it right and to get it running at a decent speed on a mobile device because, well, if you just use a normal CPU and try to process that amount of data, it's just too much. So you need to have a specialized chip. This is the holographic processing unit, which runs those point cloud processing, gesture recognition, and so on specialized hardware. And that's how they can achieve those amazing frame rates. Quick about the input. I'm sure you're aware of that, how that works. So you put the device on your head, and you rotate your head. And that's the gaze. That's your head rotation. And then think about you have like a laser pointer, like this guy, attached to your head. And you see where the laser is pointing at. So that's your gaze ray, basically. That's where your interaction focus is being set. A couple of years, we probably will have eye tracking in those kind of devices. So you can just look around and move your eyes. Recently tried out a prototype from Fraunhofer Institute. They had eye tracking. It was pretty awesome. So it was nice. I think that's where we're going in a couple of years. Right? So you need a way to set your interaction focus. Right now, that's really your head rotation. And then, well, you need to trigger the action. So think about like the AirTap gesture, the famous AirTap gesture, like a mouse click, basically. So gaze is like your mouse cursor in 3D, and AirTap is like your mouse click. You have a bunch of other gestures, but this is really the most important one. Since you're a bit limited in terms of input with the device, voice and voice user interaction plays a huge role. The device does a great job. It has a microphone array built in, so just sitting above your mouth, and the device can recognize very well what you actually talk about. It also has Windows 10, so Cortana speech recognition engine does a decent job. So how can you develop for mixed reality? And again, when I talk about mixed reality, it's not just the HoloLens, right? So this is also those immersive mixed reality devices. They have the same API set. And with Windows 10 Fall Creators Update, that is part of your Windows desktop machine as well. So that's how those VR or immersive MR devices actually work. Well, Windows 10, Direct 3D. The HoloLens itself currently supports Direct 3D 11. So you can use that with C++ or C#, or you can make your life a little easier, use middleware like Unity. Unity really comes from the game industry, but they put so much effort now these days, and it's used really for a lot of not just game, but actually really professional and industrial use cases as well. They have built-in XR support, so again, that's how Unity calls the overarching umbrella term for mixed reality platform of HoloLens, but also like Oculus, Vive, and so on. So that's how Unity calls that. It's XR, that's the umbrella term. Built into Unity 2017, has full support for that. Also ARKit, ARCore is all supported by Unity. And I can tell you, a lot of the applications you can find in the store, also made by Microsoft. Pretty much every one of those is built with Unity. There are a couple that are built with custom engines on top of Direct 3D, but most of the people really use Unity. A lot of the material tutorials all based on Unity. So safe bet to go with Unity. Free for personal use. You can get started, download Unity, build your own applications, and for HoloLens you have the emulator. Or like I said, they share the same API set like with the immersive headset, so you can buy one of those for $299. And get started with developing. But again, you also have an emulator for the HoloLens, so you can get started with developing for that. All right, let's switch to demo. And I put on the HoloLens here, and I will launch an application on my computer so you can see what I see. And I will show you the demo as it's being readily built, and then I will show you how you can build that yourself. Okay, so let's switch to the HoloLens app. There we go. Live stream. All right. How's that? Works pretty decent. It's always a challenge, you know, with network routing and the Wi-Fi. All right, so I'm going to launch the app. I called it HoloFame because it's, well, you will see what it does. This application will show you some of the basics, but also some of the advanced things. So what we will do here in this application, we'll show you spatial mapping. So how can you implement spatial mapping, which means the device can reconstruct the room you're in, and it will show you a mesh, and you can interact with that. It will also show you interactions like the gesture, and then it will also show you the hand proximity interaction. So you can see this little red box, right? And you see how it snaps to the surface here. So when I look at it with my gaze ray, it snaps to the surface, and when I'm happy with where it's placed, I can just, well, it's a bit, well, let me place it somewhere else. Yeah, you can see that the reconstruction is not working that great because we have that really black, you know, surface here. So that means there's not a lot of contrast. All right, that's okay. So I tapped, as you have seen. So now it's stable at this position, and I can also use a tap and hold gesture to bring it a bit up. So I then have to crouch down, and then I'm going to show you this hand proximity interaction. So now the device actually also tells me the world coordinate of my hand because it's recognizing my hand. Oops. Where's it gone? Nice. There we go. Back again. Yeah, it accidentally tapped, I guess. So let's try to move my hand into that wet concrete here. And you can see I move my hand, and I can actually do an interpolation between it. So I can really use the world coordinate of my hand and use that for some interactions. All right. So that's what we're going to build, so you know how it looks like. Let me close the app and put off the HoloLens. I could actually wear it while I'm going to show you how to code for it, but that's just awkward. All right, let me stop the stream here for a sec. But hey, you guys look awesome. All right. Good, so this is Unity. Again, not going too much into the basics here. I would assume you know how to set up Unity scene, how to configure it for the HoloLens. So, okay, let's look into this script here. And all of that code is up on my GitHub account, so you can get the finished scene right from there and use that as a starting point. All right, so we have a camera, which is the user's head with the HoloLens. We have a light to actually light and shade the virtual objects, right? And then we have this placement container, which is, well, this 3D object. And this 3D model was made by one of my team members, Jesse Havens, also a 3D artist. And he was so nice to make me that 3D model for the demo. And this placement container, well, it's a game object as a kind of a parent object. And then under that, we have the actual geometry here, right? You see the geometry there. So, all right. Let's add spatial mapping first. So don't worry about the placement container. Let's add an empty game object and call that spatial mapping. Reset the position. You see there it got some weird position here, so we reset the position, so it's at the origin. And then we can just add the spatial mapping renderer and the spatial mapping collider. So that's easy. So there are built-in components, I think since Unity 5.5, yeah, 5.5, I think. And so you don't have to import any stuff from an open source project. It's built into Unity. All right, so spatial mapping renderer, what does that? And you can have two different render states here. So the one is occlusion, which is basically being used to hide your virtual objects behind real-world objects, right? So occluding virtual objects. So it's using the spatial reconstruction to occlude objects, or you can set it to visualization. Well, then you can see the spatial mesh and the map around you with different colors. Then you have a bunch of different settings. This one is important, time between updates. That tells you 2.5 seconds currently. That's how long it takes until the spatial mesh is being updated. So if I take this chair, move it there, give it a couple of seconds, it will catch up and the spatial map is being updated, right? But if people all walk by fast, well, that's not going to be in the spatial map. Then we have a couple of things here, level of detail. As you can see, it's the quality, of course. Higher level of detail also means higher computing power is needed. And then we can say what kind of bounding volume we're interested in. Currently it's set to a bounding box, 4 by 4 by 4 meters is the half of it. So the bounding box is actually 8, 8, and 8. And that's basically the size of where the spatial mapping is being recognized around this point here, around the position. Right, so that's just for the rendering. And then this one is important, the spatial mapping collider. So this is being used for the physics collision. Because what I do here when I have this gazing, I'm actually shooting out a bunch of rays from the camera, and where those rays hit, the camera's user's head, right? And where the rays hit a point, then you have a collision, and that's where you can place that object. That's why you need this spatial mapping collider. Pretty much the same settings here. Instead of having some rendering setting, of course, it has some physics material, so you could also use that for physics interactions. I made some other demos before. I'm not sure if you have seen that, like where you could shoot, like, actually I had a meatball demo. I should have brought that to Sweden, where you could shoot meatballs to people. But, well, I did that last year, so let's do this one. Spatial mapping, so pretty easy to set up. Now we could have a spatial mapping, so that's straightforward. Now let's look into how can we implement the actually gazing and gesture. So I wrote a different script for that. And again, it's all in the GitHub repository. You can get all of that from there and take a look after this session. So I take this placement behavior, and let's open Visual Studio here, and I'm going to show you some of the code. All right, how's that? I think, can everyone read that? Awesome, great. So we have, first of all, a gesture recognizer. This is a built-in API, the Unity, which is, as you can see, XR-WSA, which stands for Windows Store App, which is Unity's terms for saying it's a universal Windows platform. So it's a mapping, basically, of Unity to the HoloLens APIs. So that's where the gesture recognizer comes from. We instantiate that. I will quickly go over that, because I think Laurent showed it as well. So we have the tapping, right? You just attach an event handler here, and this event handler is doing the following. It says a flag, it inverts the flag, a Boolean flag is placed or not. And this flag is used in the update method. The update method is called in Unity every frame, so 60 times per second. And we check, okay, is placed true? We don't do anything, because the thing is meant to stay at this position. If not, we do this ray cast I mentioned, so we shoot a bunch of rays into the scene. Then we get the closest hit, so I sort that here with an expression, and I get the closest hit, which is the closest to my head, basically, use that position and the normal vector, so the orientation, to actually assign that to my object, and that's how I can place it. That's pretty much all you need, really straightforward to do. Okay, so we have gazing, we have spatial mapping, we have the gesture. So now what about this hand proximity interaction? How I call it hand proximity interactions, although people might call it differently, but it's really touching objects with your hand. So how can you do that? I wrote another script for doing this, and we can just attach this one, and I'm going to show you the code of that as well. So hand imprint behavior, we assign this kind of a 3D model here. You see, I'm assigning this one here as a reference to this 3D model. And then I also have some parameter controller added here. But let's look into the code. What's inside of it? All right, so first of all, I forgot one thing. I forgot to attach the collider. So let's attach the collider first, because we need a box collider around our nice 3D object here. You see, this is the box collider, the green box. It's a bit too large. So let's change the size. Let's change it to one that actually fits it. Oops, what's going on here? The focus is not set. And a bit smaller. All right. And doo-doo-dip. Got this guy. And you see now it's fitting pretty nicely. So we will need this collider to actually test the hand against the box, because otherwise we could do it still, but the box collider makes it a lot easier and gives us a lot of nice built-in features, if you will, right? So let's take a look. In the start method of our script, we get a reference to our collider, and we also attach an event handler to the so-called interaction manager. So an interaction manager, well, it provides a bunch of event handlers. This one is really called if an interaction is triggered. And you can see, you can check the kind here. There are different kinds. So there's, for example, one for the controller, voice, and so on. We are really just interested into the hand. And then we use this API here, try get position. And this gives us the hand position as a vector 3. So we get the X, Y, and Z coordinate of the hand in world space, right? So we use that hand position to test it against our collider. does our hand actually, is it inside the collider of our box? Yep, it is. So what are we doing? We do a bit of math here. Basically, I transform that or normalize it into a value from 0 to 1. You know, how far has the hand traveled into the object, pretty much. And I use that value to use that for an interpolation of the so-called blend shape weight or morphing. Because what we have, this 3D model, is actually two models, right? We have the flat one, and then when the hand is fully in, it's a so-called skinned mesh, so you can interpolate between the two. And we just use the value, how far the hand has traveled, to set the value there for the interpolation. I also wrote a quick custom shader that uses two different textures, diffuse textures and a bump map or normal map, and I interpolate between those two and fade, because we have a different bump map when it's flat and a different one when it's like when the hand is fully inside. So I interpolate between those two so it looks a bit nicer. Again, all the code up on the GitHub, so you can also check out the shader, but it's really just simply interpolating between two textures there. All right, so that's how you can implement a hand imprint, or how you can use this hand proximity interaction. Not too hard, really. The main important piece is this here, right? Test for the hand, get the hand position at world coordinates, and do something with it. That's easy. All right, that's all I wanted to show you, because we just have 40 minutes in total, but I also want to show you some of the best practices. So let's switch back to the slides here. And yeah, here's a video. So you see, this is actually in LA, in front of the Chinese theater in Hollywood. So I was the weird person that was wearing a HoloLens in front of the Chinese theater and made my holographic hand imprint there. But it's in Hollywood, so no one cares anyway, because you just look weird and everyone doesn't care, because there's like even more weird people all over the place. All right, I just had the video to, in case the demo failed. But let's dive into the lessons learned. I'm going to show you some of the apps. Unfortunately, I cannot show you all of the apps because of time, and second, because of NDA with different clients, but I can show you the most interesting ones, unfortunately. So here's one we did. It's called the Chem Plant, and I think Lauren showed it as a live demo as well. The Chem Plant, what we did here is a visualization of a chemical plant with the HoloLens. Well, that's not so interesting, but what we can show is sensor information of the chemical plant. As you can imagine, it's full of sensors, so we can show that inside the plant. You can also scale it up to a 1-to-1 scale. So you cannot just show it at this small mode. You can fully scale it up, and then you're inside the plant and can look around. That's really awesome, and that's one of the main features of the HoloLens, is being this fully immersed, being really in a different setting. Lesson learned here is provide the user a way to dynamically interpolate between those two scale modes, right? You cannot just launch the app with the full scaled model, because this would just like throwing geometry in the face of the user, because they're wearing a screen right in front of their eyes, right? That's not very convenient. That's really not nice. So what you should rather do is launch the app with a small model, like I showed you in the demo, right? Allow the user to place it somewhere, and they can see the whole model at once. So it fits into the frame, it fits into the field of view. And then you can provide them a way to dynamically upscale, to have it at the full range scale, and then you should interpolate between those states, right? Don't just show it small and then huge, rather scale it up slowly, because in the real world, objects also don't just like be all small and then huge. They grow. So you need to provide a nice transition between those two. Another app we did for automotive client in the US. Well, that's an assembly line pretty much. So the client, the use case, they launch a new product, and that product, of course, needs to have a new assembly line. So they need to design that assembly line, and they need to be able to test it out. So instead of like building all of that upfront, we built them a HoloLens app where they can use holograms or virtual objects to try out those assembly steps, which is much easier to try out than having the real objects. You can see we have this hand proximity interaction, like this guy is using his hand to place this axis on the frame. Works really well, and lesson learned is definitely those hand proximity interactions at the 1-to-1 scale, real-world scale of the object. This is awesome. It really feels as a very natural user experience. So make use of that if it makes sense in your application, right? Of course, gaze-based and then unit gestures make sense as well, but if you have like direct interactions, definitely use that as well. As you can see, we also allow the user, here you have the tools, the racks and bins and whatnot. We can also allow them to replace them, to reposition, to optimize the assembly steps, to try out different stuff, right? It doesn't make sense to have my tools here or there. So good stuff, worked really well. Client was happy. All right, another one recently finished. It's well, it's for a client that does automotive seats, as you can see. Yes, so you see the holographic hands here, and actually this piece here, this is also a hologram. So we render the hologram or the virtual objects on top of the real-world objects for a training purpose, so people can learn how to assemble a seat. And when I was there and tried it out myself, tested it, okay, does the application actually work as it's supposed to be? I was able to do those assembly steps without having any further training, right? So that really works. That really works well. And overlaying holograms on top of real-world objects is an amazing feature. You definitely should use that. That's really where this augmented reality makes a lot of sense, right? Not just showing like objects floating in space, like stickers, but actually having them connected with real-world objects. Use that. Lesson learned. So how do we position those? We use a fiducial marker. It's not here in the picture, it's somewhere here. So there's like a little QR code or any marker you want to use, an AR tag, an AR marker, and that's how we can find initially the reference position. After that is done, we switch it off, the camera, and just use the spatial understanding of the HoloLens. So it will stay in the position, but for the initial placement, for the audio placement, we use a little marker. That works really, really well. Though we still provide a mode for manually fine-tuning that, right? Sometimes it's a bit off because they didn't like attach the marker correctly or whatever, lighting conditions. So we provide a way to with tap and hold to do fine-tuning on all of that. Works really well, and I can only recommend to do that. Another piece for an automotive client in Germany, actually. Yeah, well, you can see it uses machine learning as well. So here's the use case. This is the guy wearing the HoloLens. He takes a photo. This is the photo he has taken. We send that to a backend, and that backend runs a machine learning, a deep learning, a neural network in the end, right, for image classification. So what we do there, this backend was trained for image classifications on a bunch of photos from the disc brake, for example, and then it can automatically recognize it. We pulled some data from a database, like, okay, it's this disc brake, has this and that properties. And we can also show a schema graphics in the field of view of the user. So the user sees that panel with all the information. Plus, we can actually play a video how to assemble it. So we can play a video into the field of view how to assemble that. And, well, you wear the device on your head, so your hands are free, right? But what you have with the HoloLens is actually wearing a computer on top of your head with the screens. How cool is that? So you have your hands free for doing real actual work. Yeah, it worked really well. You probably heard there is some news about the HoloLens V2, and the official news so far is they will have a new HPU, a new chip, and that can apparently or have some AI capabilities. So let's see what happens there, right? So bringing that from the backend into the device, that could be awesome, like running pre-trained neural networks on the device. Well, I'm in for that. Yeah, good stuff. Another one, you see, we do a lot with automotive clients. So here's a tire. Wow, a tire. Bridgestone is the client here in this case, actually. And we did an app for them, and we showed at the Build conference earlier this year where we can augment a real-world tire. I'm going to play you the video. Since we don't have much audio anyway, I'm going to talk while it's playing. All right, so this is a capture at our demo booth. You see, this is my colleague Justin. He's wearing a HoloLens. So let's play that. And I'm going to tell you about this guy later. But let's focus on Justin here wearing the HoloLens. Look at it. He's actually now looking at this tire. And you see there's no marker. There's no fiducial marker on the tire. So after a couple of seconds, it's being recognized. So you see the silhouette there. So it's recognized as the tire, and we can augment it. So what we use here is we got early access to the Bavaria model targets. And Bavaria model targets is allowing you to do object-based tracking. So you can use a CAD model, any 3D model actually, and use that as your marker. So no sticker, no QR code, nothing. You can use a real object, CAD model of that object for tracking, and that's where, in general, AR marker tracking is going, or AR tracking is going to be. It will all be object tracking in a couple of years. So, oops. So what else to say about this one? Sorry for that. Let me go back. All right, let's go. yeah, look at it again, so the tracking here. What I wanted to mention is, of course, you have limitations in terms of the 3D model for the object tracking. So the CAD model, we cannot use your million polygon count CAD model, it's just not going to work on the lens. So 100,000 polygons is the maximum, less is even better. Also the lighting is important, so you see we mounted this light here, so they have a bit more contrast on the actual surface of the tire, so that the computer vision algorithm that runs the object tracking has something to attach to. You see this guy here, well, he just disappeared. That's my colleague Rod. And we are working on a technology called HoloBeam. I'm going to show you that in a couple of slides. Basically what we can do, we can use a depth camera and capture him and then record those frames and play them back. We can also do real-time streaming. I'm going to show you this in a second. But yeah, this is the version. We call him HoloRod now. And HoloRod is he's giving you explanation about those tire components, right? So, of course, that's much nicer than just hearing a sound or reading text, like actually a person is explaining you about those components. We also paid a lot of attention to the visuals, so it's really nice shading, all done with custom shaders pretty much to get a decent rendering frame rate. All right, next one, big data visualization. We did that for a client that has a software for actually security incidents and security threats. I'm going to speed up a bit here. But anyway, you can see the green dots. Well, these are, all is good. These are basically nodes in a computer network, if you will. So these are good. The yellow ones might be unpatched windows. Well, red ones might be an attack, whatever. So you can imagine, let's generalize that a bit more. Huge data, visualizing that in 3D, having a stereoscopic display where you can actually sense the depth, that's really awesome. But the challenge is, of course, it's tons of stuff you need to render. So what are we doing here is we use game object pooling, so not just instantiate new game objects all the time, and of course also custom shaders. So all the rendering here, the lines and all of that is all custom shaders. So it's directly emitted on the CPU and the GPU, and that works pretty well. So if you have those huge amounts of data, you definitely need to invest in custom shaders. There's another piece, HoloFlight, our real-time flight data visualization. I'm going to skip that real quick. We're using real-time flight data, like I said. And yes, that's a couple of lessons on there. You can see we have those planes. When you gaze at them, there's actually a larger bubble around it. That's our collision volume. So if you look at them, it will be very hard to select them. So we use a larger collision volume around it, makes it easier, better UX. We also actually place sound, so spatial sound at the plane's location in 3D. So even if you don't see them and you can hear but you can hear the sound of the selected plane, you know immediately where to turn your head because you have those tiny speakers and the spatial sound algorithm built in that really makes you sense where the sound is coming from in 3D. The UI you saw there in the back, we can also place it individually to lay out the workspace. We use real-time flight data, but we can also cache the flight data in our own Azure backend, pull it from there, play back the cache data much faster and do things like this, like let the trails stay and see where those flight routes typically are. All right. Well, there's even more outside of the box. What I'm trying to say with this one is the HoloLens is packed full of sensors already. It's insane. But we actually can augment that much more, and we can use external sensor data. We're surrounded by sensors everywhere, right? IoT is one of those nice buzzwords which defines that we're basically surrounded by sensors. You have smart home devices probably, but we can also stream in data because the HoloLens has a Wi-Fi stack. It has a really good networking API where you can pump a lot of data. It supports Wi-Fi AC, which I'm using here for the demo. Here's a piece where we were using the Kinect to augment the person with the, Let's skip that for a second, but you can imagine it. We're using the skeletal tracking of the Kinect to overlay that on top of the person. Works pretty well. And so here's HoloBeam, what I mentioned earlier before. Here's a recording. It looks like a 2D video, right? But in fact, it's also using a depth camera. So we use a depth camera like the Kinect or an ORBAC, or there are other 3D cameras on the market. And we can scan a person in real time and use the depth data to reconstruct the point cloud and render that in real time. And as you can see, when the camera is moving, that's not just a 2D video. It's actually 3D, right? You can see the person. That's really 3D. And we also have different modes we support. Here's a test I did the other week with my colleague in Seattle. So you can see I'm throwing this little object here. And take a look what he does. So if you see, there's almost no delay. So we can stream that with a bandwidth like 3 to 6 Mbit. Depends. It's adaptive streaming, what we developed. So we can even go as low as 1 Mbit. Of course, the quality is not great then. But the general, it's full HD mapping in real time without any issues streaming it under the Atlantic or even worldwide. Here's another test we conducted the other day. Here's India. So they see me and my colleague Justin. Seattle sees me and Ashik from India. And I see Justin from Seattle and Ashik as well in real time as a hologram. The video really don't give you the right impression. It looks okay. But seeing it with your own eyes, with a stereoscopic display, you can actually sense the depth of the people, like the nose and so on. So that's a whole different story. And yeah, telepresence. We also have it running in the immersive headset into those VR devices. You see we have a different background here, so you can integrate that into custom solutions. That's how we started 1 year ago. So much lower resolution, and that was really just local network. Now we achieved the using adaptive streaming. So lesson learned here. We're using WebRTC now. We forked that. That's a project mainly developed by Google. But we forked it to implement our custom depth encoding algorithm, and we hooked it into the video stream. What we also do is, of course, we pay a lot of attention that it's running at the full frame rate on the device. So that takes a lot of work. What we're doing here is a custom geometry shader that emits all those points directly on the GPU. That's the only way how you can get it running at a decent frame rate, and a bunch of other tricks. All right, let's speed up a bit, because I'm really almost at the end of time. Top 10 HoloLens development recommendations. But I actually asked Carsten, the gentleman that's after me, if I can go 5 minutes longer. Is it okay if I go 5 minutes longer? Yes? Good. Yeah, I know there's lunch, but it's like you have to make a decision in life. So lunch or HoloLens? HoloLens. All right. First recommendation, leverage its uniqueness. So what I'm trying to say here is we have this device with those displays, see-through display, waveguides. That's amazing what they achieved here, and let's use that. Let's actually augment the real world of the user, not just show stuff somewhere floating in space, actually place that, because we have the spatial mapping. We have the SLAM algorithm that runs here with those sensors, so we can augment the real world of the user. We can place objects, so use that, and also make use of the multi-lens feature, which means when you wear the device, other people, we could all wear a HoloLens, and we could have a shared network connection, and then we could see the same holograms, the same virtual objects together, but also see us each other, right? Try that in VR. That's not possible. So that's a very unique feature of the device. So take advantage of this. And that's really huge also in professional use case scenarios. People just don't want to sit in a meeting with a VR device on and like have a review of that. That's not just going to work, right? But doing that with the HoloLens, that's possible. So use that. HoloLens is really a mobile device, which means it has also limited computing power. Of course, all of that computing, it does so many stuff, and it's still amazing that it runs on the battery for 2 to 3 hours. And yeah, but again, constraints, and especially in terms of rendering. So what you need to keep in mind is, of course, if you have like 3D models from your design department or from engineering departments, they all have CAD models. And they always tell you, oh, we can just give you those models, and then you can render them, you have them ready. It's never the case, because they never just render like they would imagine they would do, because you cannot render a million of polygons on the device. So there are different strategies for reducing those. I gave a talk about that at the Vision VR Air Summit and at AWE. You can find them on YouTube. It goes a bit deeper. But basically, you can use a manual model reduction, or you can use automatic with tools like Simplegon and Umbra. They all have advantages and disadvantages. But again, take a look into that. Another important piece is the device is really full rate bound mostly, which means rendering lots of pixels and having an expensive pixel shader for each pixel is not going to give you the full frame rate. So you need to be careful to have a very simple pixel shader. What I showed you is really custom pixel shaders we wrote to actually get a decent frame rate running on the device. So definitely take advantage of that, and yeah, you might have to get some specialized folks that know how to do shaders or learn it yourself. Design for the holographic frame. I mentioned that earlier. So you have this holographic frame in Microsoft terminology, or other people would call it field of view. So keep that in mind. And when you launch an app, show the user the full hologram at the full scale. For example, you have the tire I showed you. So what we do with the tire, when it's placed, we allow the user to place it, but we basically attach it to the gaze ray, and it's always at 2 meters distance at a scale that fits into the full frame. So the user is not seeing a cutoff. And that gives, of course, you not the impression that you're not seeing the whole thing. So, show it at this scale, then allow the user to place it, and then they can just always walk closer to it, right? And see it in a higher scale, or provide a way to scale it up dynamically. That's really important. Think outside of the box. I just mentioned that. Think about other sensors. We have really high and nice connectivity. We also had an app I couldn't show you where we used a companion application. So you have a tablet that is connected with the HoloLens, and you can do like complex input data on your tablet and use just the HoloLens for visualization, right? So there's a lot of stuff you can do with the networking. Let it focus on the important things. So this is really more developer-focused recommendation. We have an API in the HoloLens called stabilization plane. And that stabilization plane allows you to define a point in the normal, like a plane, a 3D plane, where the HoloLens will spend most of the time to keep it stable. So if you set that, if you have those apps where you just have one, I call it hero hologram, like just one of those virtual objects, set the stabilization plane on this point, and let the normal face the user. So basically, when the user walks around, it's always the plane they're facing, and that will make sure it doesn't jitter. That's really important, and it's often overseen. So take a look. It's really easy. It's one call. I used it in the sample as well. I haven't shown you, but you can see it on GitHub. Just one line of code. Really straightforward. Get your holograms anchored. There's an API in the HoloLens called World Anchor. You can also attach that to a 3D object, and that will make sure that the hologram is always at the same position. So even if you leave the room, enter it again, it will always be at the same position. And you can, even better, you can persist those. So when I'm home, go in my office, turn on the lens, I will have holograms on my office wall because they are persisted. It can recognize via pattern recognition the room it is in. Really good one. World Anchors also makes sure that your holograms are stable, so use that. Share your holograms with the world. Well, you can, first of all, you can submit them to the Windows Store. So as a demo, we use it a lot for marketing purpose. So a couple of our internal demos, we just publish them on the store. It's really easy to give them to customers. Here's a link, install them on your lens and try it out. Because seeing is believing with this device. It doesn't look anything close to the video. What I showed you with the live streaming, it's called mixed reality capture live streaming, but you can also capture it and record those. Especially important when you want to share it with a client, right? But the MRC, as it's called, has some downside. First of all, it drops the frame rate to 30 frames per second. So it doesn't run with 60 frames, it only runs with 30 frames because it also needs to do the video encoding on the device. It's a huge downside. And also what you have seen, it's really not the real representation of the hologram. So the rendering is not using additive blending, so the device actually uses additive blending. What they use in the MRC is not additive blending. It's alpha blending, so that's wholly different. You can use a tool called Spectator View. You might have seen that at Microsoft Keynote. They have this special camera setup. Microsoft released that as open source, actually. So you can use a HoloLens, attach that to a DSLR or any camera, and use that for recording your holograms, and then you have much more control, and it looks much better. We also provided our own solution based on that called Miro, where we can, we rewrote the capturing software a bit, because we wanted to actually be able to move the camera around and have things like that. Don't reinvent the wheel. There is the mixed reality toolkit out, so use that. It's an open source project, provides you lots of awesome scripts, examples, shaders, which you can use to rebuild your app on top. Not rebuild, but build your app on top. And also, the Unity Asset Store has a bunch of, especially for VR, but you can use a lot of those VR assets as well in your HoloLens applications or augmented reality. Offloading is an option. So I mentioned 3D model reduction, like you need to reduce the polygon count, but there's another option. It's called holographic remuting. What this allows you is actually to stream in the position and all the sensor data from the HoloLens to your computer, and then your computer recomputes the scene. It runs in Unity, so Unity is actually rendering your scene based on the input data from the device, and then it streams that back as 2 video streams, one for the left, one for the right eye, and that allows you, of course, to do much higher quality renderings, but has a downside that you have latency. Latency is around 10 to 20 milliseconds or 30 to 40. It really depends what networking setup you have. If you have a decent network setup, you can actually get a very low latency, and it makes a lot of sense for static scenes. If you have those architectural design reviews where you just have a huge 3D model, which is mainly static, not a lot of animation, not a dynamic going on, definitely this holographic remuting is something you can look into. Yeah, think about mixed reality beyond the HoloLens. I mentioned that indeed we don't just have the HoloLens, it's a whole platform Microsoft is releasing. And think about those immersive mixed reality devices which allow you to use the same API set, and you have options to check if it's an included device or is it an holographic device. And then, for example, you could enable a skybox or some ground plane or whatever in the VR world, and don't do that in the HoloLens world. So that's really something to keep in mind. Build it that it's a bit more dynamic and can adapt to the platform. I mentioned that. I'm running out of time, so we'll skip that. Thanks for your attention. I think it's an amazing time to be working with mixed reality. We will really get close in a couple of years also when it comes in together with machine learning. It's an exciting time. The device will have much more understanding of the world it is in, not just like the spatialness, but also the actual objects. So exciting time. I'm sticking around for a bit. You can just ask me any question you want. Also, here's my Twitter handle as well, my blog, and here's the demo I showed you. You can get all the code from there. And with that, I wish you a pleasant lunch, and thanks, and please press the button out there.